So today I will talk about rough foundation on soft soil and the problem engineers face when designing them. So one major challenge is making sure the foundation can safely carry the building load. Soft soil tends to settle over time, which can affect the building stability. So if the settlement is uneven, it can cause crack or structural damage. Because of this, traditional design method may not always give accurate results. So to deal with this problem, we use PLAXIS 2D, a computer program that helps us better understand soil behavior. So the advantages is it gives more accurate prediction of total and uneven settlement. So it shows how pore water pressure change over time, which improve the accuracy of result. It model the interaction between the soil and the structure more realistic. So using the PLAXIS 2D helps the engineer design safer and more reliable rough foundation even when the soil condition are poor. So moving on the project objective, our main goal is to understand how a rough foundation behave on soft clay. So firstly, we will study the settlement of the rough foundation on soft clay. We will estimate the long-term settlement caused by soil consolidation by simulating how pore water pressure decrease over time. So this helps us understand how the foundation settles gradually and how it affects the structure. So next, we will examine differential settlement and tips. Differential settlement happens when different parts of the foundation settle by different amounts, which can cause damage. We will check whether this uneven settlement leads to tilt and assess its impact on the building stability. Finally, we will compare the result with serviceability limits. This ensures the structure remains safe and functional. We will check that first, the total settlement is within allowable limits, and the second, the differential settlement and tilts are within acceptable limits to prevent structural problems.
We'll proceed with the problem statement. So what is the problem statement? The soft clay has a low strength and high compressibility. So when the rough foundation on top of the soft clay, it may experience a large settlement. So when this is happen, it is called the consolidation settlement, which is it is occurs over a long period. There's also a differential settlement that can cause the structural damage. So there is one method, which is the conventional method that called the Terzaghi one-dimensional consolidation theory, where it is oversimplified. So to investigate this more detail, the advanced numerical analysis is required for accurate prediction. So what is the limitation of conventional methods? So the limitation is it is assumed as a one-dimensional consolidation, and this conventional method assumes the soil is a uniform soil conditions. Next, it is cannot model a soil structure interaction, and it is unable to predict the differential settlement accurately. So it is do not consider the pore water pressure dissipate over the time. So it may lead to inaccurate settlement prediction.
This project, we adopt numerical analysis approach using PLAXIS 2D to investigate the settlement behavior of a rough foundation on soft clay, with particular emphasis on long-term consolidation settlement. The soil profile is modeled as a three-layer system. The top layer consists of sand under drain condition with a thickness of 2 meters, representing the surface layer. The middle layer is soft clay under undrained conditions with a thickness of 15 meters, which is the critical layer governing settlement behavior. The bottom layer is bedrock under drained condition with a thickness of 13 meters, providing a relatively stiff support layer. The rough foundation is modeled as a plate element in PLAXIS 2D. It is assigned a plastic behavior to present realistic structural response with a thickness of 0.8 meter. The groundwater table is set at 1 meter below the ground surface, allowing the influence of pore water pressure on consolidation behavior to be considered. A uniform vertical load of 150 kPa is applied on the rough foundation to represent the structural load transfer from the superstructure. Appropriate boundary conditions are applied to ensure model stability. The base of the model is fully fixed, while the vertical boundaries are restrained from horizontal movement, but allow to vertical displacement. A consolidation analysis is then carried out to simulate the settlement over time due to the dissipation of excess pore water pressure. The results are evaluated in terms of total settlement, different settlement, and foundation tilting and are compared against typical service limit criteria.
Moving on to our result section, I'd like to focus first on the serviceability limit state. We ran a consolidation analysis over a 50 years period to see how the soil and foundation would behave long term. On the left, you can see the consolidation settlement result. The simulation predicts that after 15 years, the center of the raft will settle by approximately 10.4 centimeters. On the right, we have the access for water pressure control. This image proves that our drainage setup is working correctly. You will notice the blue zone at the very top and bottom. This indicates that water has successfully drained out of the soil at the boundaries. Next, we move to the quantitative verification of our design. On the left, we have the time settlement curve. This graph tracks the vertical displacement of the raft center over the full 50-year period. On the right, we have the safety factor graph from our VC reduction analysis. Together, this graph confirms that the design meets both the serviceability limit state and the ultimate limit state. Next, I will talk about the discussion part. Firstly, about the overall settlement. Overall settlement is about 104 mm. The raft foundation experienced significant compressibility under a load of 50 kPa. The settlement shows that deformation happened beneath the raft foundation while surrounding ground experienced the smaller movement. Even though the settlement is large, the serviceability is controlled more by uneven movement than amount of overall movement. The raft foundation spread the load over the large area and increased the foundation stiffness, so it tends to reduce the differential settlement. For the differential settlement, which is the difference between the maximum settlement and the minimum settlement of the raft foundation on soft clay. It is an important parameter because it helps indicate whether the structure can still perform satisfactorily, even if the overall settlement is large. Over the graph, the differential settlement is approximately 10 mm. This means the raft foundation experiences about 10 mm of uneven settlement across its length or width. For the tilting calculation, use the equation below, and then substitution of a value into the equation gives data 0.0005. This value is smaller than the common serviceability angular distortion limit for building, but it still indicates that the foundation is safe from the tilting.
In conclusion, the foundation experienced the large total settlement on soft clay, which is 104 mm, but with limited differential settlement, which is only 10 mm. So it remains acceptable in serviceability perspective. Next, because the rough foundation is relatively large, which is 20 meter, the settlement is mostly uniform. So the value of the settlement also indicates that the rough foundation can be effective in improving the settlement uniformity on soft clay. All the conclusions are acceptable in terms of serviceability limits, but for the long-term settlement, this becomes the critical factor that requires the careful serviceability assessment, and if it is necessary, the ground also needs an improvement. So that's all from us. Thank you.